All right, well, chapter 20 is the end of a 4-chapter sequence, 17, 18, 19, and 20, where we have been looking at carbonyl compounds and two types of reactions with those carbonyl compounds, in particular, nucleophilic addition and nucleophilic substitution, so nucleophilic acyl substitution. And so in this chapter, we're going to be focusing primarily on carboxylic acids and their derivatives. And so what that entails, that is going to include these 5 different types of compounds. Carboxylic acids, of course, carboxylic acid chlorides, so these are the acid chlorides of carboxylic acids. That's where we replace the OH with a chloride. Acid anhydrides, and we'll talk about those, but those are a useful class of compounds. Esters, and so here is esters. That's where we replace the OH with an OR, and then finally amides. And so that would be those would be our 5 different types of compounds we will be talking about in this chapter. So we've talked about acid chlorides before, so we've mentioned those. I do want to mention acid anhydrides because we haven't really talked about those up to this point. So acid anhydrides have 2 carbonyl groups that are joined by a single oxygen atom. And we're going to find there's several different types of acid anhydrides that we're interested in. One is called symmetrical anhydrides, and this is where we've got 2 identical alkyl groups on either side of the carbonyls. We've got mixed anhydrides, and that's where we've got 2 different carboxylate groups attached to an oxygen. And then finally, we have cyclic anhydrides. And cyclic anhydrides are kind of in a category by themselves, in part because of how they're made and also in part of how they react. When we talk about amides, we haven't talked extensively about them, but we've talked a little bit about them. We want to classify the amides in terms of the number of nitrogen or the number of carbon atoms each nitrogen is attached to. So the smallest number of carbons we can have for an amide is going to be a primary amide, and that's because it has to be attached to at least the carbonyl carbon. A secondary amide is going to have that carbonyl carbon and 1 alkyl group attached to the nitrogen. And then our tertiary amide is going to have, again, the carbon that's attached to the carbonyl, or the nitrogen attached to the carbonyl, and then 2 alkyl groups attached to the nitrogen. So we want to be able to identify those relatively easily. So I've got a fairly easy problem, which is this one, where we're looking at the compound oxytocin, and it is a naturally occurring compound, but it's also one that can be used as a drug. And it is a polypeptide. It's a protein, and so we're going to identify the different kinds of amide linkages in this compound. So primary, secondary, and tertiary. So give it a shot before I go through them. Give it a shot and attempt to do it by yourself, and then we can go through it. All right, so let's look at this one. This one right here, it's only attached to 1, so that one is primary. So that one is primary. All right, we'll come over here. This one is secondary. So we've got a secondary amide there. This one is connected there. So we've got another secondary. This one is also secondary. This one up here is primary. All right, let's come down here. This one is secondary. All right, here we've got another one. This one is secondary because there are 2 carbons attached. All right, if you carefully look at this, this is not an amide because the nitrogen is not connected to a carbonyl. So this is an amine functional group, and it is a primary amine, but it is an amine functional group. We come over here to this one. This one is a tertiary amide, and then here we've got a secondary. All right, here we've got secondary, and then finally over here we have primary. All right, so that I believe takes care of all of them. I seem to have everything labeled. In case you're curious, what are the amino acids that are present here? We're going to start here and kind of work our way around. This one, so right here, all right, that one is cysteine. All right, so that one is cysteine. And then if we look at this one, which is going to include this nitrogen to that carbonyl, that one is tyrosine. All right, so tyrosine. And then this one, it's got a butyl group, and if at first glance you might think that that one is leucine, but this one is actually isoleucine. And so that is, this one is so that one is isoleucine. All right, this one is going to include all of this stuff here, and this one is glutamine. All right. And then over here, from here to there, that is going to be asparagine. All right. We do have another cysteine linkage that is in here, which includes this sulfur. So the two cysteines are connected to each other. I will there is a cysteine. Okay, and then this one that includes this nitrogen, this ring up to here, that one is proline. Proline's kind of an unusual one because of the nitrogen that is in the ring. All right, and we're almost done here. Here we've got a leucine. So leucine. And then finally this one on the end is glycine. All right, I thought that might be kind of fun for you guys to look at, just so we can identify the different amino acids. Not something that you necessarily have to do in this class, but it is kind of interesting. All right, so let's look at next cyclic esters and cyclic amides. And so cyclic esters we're going to call lactones. And so these are a couple of examples of lactones, and cyclic amides we're going to refer to as lactams. All right, we'll find that these are important structures for organic chemistry. The beta lactam turns out to be very important for antibiotics, and we're actually going to look at that a little bit later in this chapter. So it turns out that one is fairly important, as I mentioned, for antibiotics. One thing I'll mention is that you can tell what kind of lactone or lactam it is based on how many carbons you have to have between the carbonyl going around to the other linkage, in this case the oxygen, and over here the nitrogen. So if there's 3, it's a gamma lactone, so this one's a gamma lactone. If it's 4, it's a delta lactone. If it's the lactam, here we've got 2. This is a strange system and kind of unusual, but that's a beta lactam, and as I mentioned, it's very structurally important for antibiotics. And then this gamma lactam has a 5-membered ring. There's 3 carbons in between the carbonyl and the nitrogen. All right, so now we want to look at nucleophilic acyl substitution. This is something that we talked about initially back in chapter 17, and then we discussed it some more in chapter 19, but it bears mentioning again, so at this point you're probably pretty used to seeing it. We're going to talk about it quite a bit in this chapter, and here in this chapter we're going to include, in addition to chlorides and chlorides and esters that we've talked about previously, we're also going to include carboxylic acids, acid anhydrides, and amides. So one of the things we're going to focus on in this chapter is looking at these different substituents and what does that do to reactivity. And we're going to find that these are vastly different in how reactive they are. So some of these are going to be very reactive. For example, the chloride is very reactive. And some of these are going to be far less reactive. For example, the amides are much less reactive. All right, so this figure should look familiar by now. When we're talking about structure and bonding of carbonyl compounds, we're going to have an sp2 hybridized carbon with a approximately 120 degree angle. It's polar. That polar imparts reactivity. Again, this is something that we've talked about many, many times. So the electrophilic carbon is going to be a location where we get nucleophilic attack. And in this chapter, we're focusing primarily on compounds that have a potential leaving group, and that leaving group can be any of those things that I just mentioned: chloride, OH, OR, a carboxylate leaving group, or an amine leaving group. So we're going to find that the stability of this compound, in part, is going to be determined based on how stable these two structures are. So the more that our resonance structures 2 and 3 contribute to our overall hybrid, the more stable the compound is. And we're going to be particularly looking at number 3. So we're going to find things that are really good at donating those electrons are going to be very stable. That means those things that are very stable are not going to be very reactive. So let's look at how strong is our Z, our leaving group, as a base. And so we're going to find that the stronger Z is as a base, the worse it is as a leaving group. So our weakest base of these substituents that we were talking about is chlorides. The carboxylates are going to be are a little worse, but still pretty good leaving groups. We're going to find hydroxides and alkoxides are not great leaving groups, but for purposes of nucleophilic acyl substitution, they may be just fine as leaving groups. And then our worst leaving group is the NH2 minus and the related compounds to that. And so that NH2 minus, it's going to be difficult to remove that. However, it's definitely possible. It's something that we can do. So as I mentioned a little bit earlier, the weaker something is as a base, the better it's going to be as a leaving group, and also the less stable it's going to be. The stronger something is as a base, the better or the more stable it will be, and the worse it will be as a leaving group. So stability of our carbonyl compound will increase as the basicity of that leaving group increases. And here we can see the pKa's for each of these, of the conjugate acid for each of these items. The lower that pKa, and so in the case of HCl has a pKa of -7. It's a very strong acid. So in that case, chloride is a very stable leaving group, which means that the compound that contains the chloride, the acid chloride, is not as stable. And then as we go down the list, this one down here at 38 to 40, that one is not a great leaving group. So not a great leaving group because this is not a very strong acid. And since that's not a very strong acid, in fact, it's a pretty lousy acid, that means that this is a really, really poor leaving group. All right, so the weaker the acid here, the stronger the other thing is as its conjugate base, and the worse it is as a leaving group. So you will want to memorize this order. And you can think of it in terms of the pKa's, or you can think of it in other terms if you wish, but you do want to have the order of these memorized. So this is just to state what we just said. The better something is as a leaving group, the less stable the carbonyl compound is going to be. So acid chlorides are not very stable. Anhydrides are a little bit more stable, but they're still pretty reactive. Carboxylic acids and esters are about the same in reactivity because the OH minus and the OR minus are pretty close to equal as far as leaving group ability. And then finally, amides are going to be the most stable because it has a very poor leaving group. All right, so now we want to look at nomenclature. So we want to discuss how to name some of these other things. And after going through the carboxylic acids, this part should be relatively straightforward, although there are some subtle little rules that we'll need to pay attention to. So, and we're doing multiple types here, so pay close attention. You might want to go over this twice when you're studying your nomenclature. We did talk about the carboxylic acid nomenclature in the previous chapter. Feel free to go check that out. We'll find that the carboxylic acid derivatives are named based on that carboxylic acid parent. So if you have an acyclic acid chloride, we're simply going to change the ending from ic acid to eel chloride. Here are a couple of examples. So we make this compound from acetic acid, and so in order to name it, we just drop the ic acid and change it to eel chloride. So acetic acid becomes acetyl chloride. All right. Here we've got another one. We've got 2-methylbutanoic acid is this if this were an OH, but when we convert it to the chloride, we're going to call it 2-methylbutanoyl chloride. So again, change the ic acid into eel chloride. If you've got a COCl substituent that's like on a ring or on some larger molecule of some sort, usually on a ring, then the way that we're going to name it is, if it were an acid, we would call that carboxylic acid. So for example, if this were an acid, we'd call it cyclohexane carboxylic acid. Well, we change it to carbonyl chloride. So this is cyclohexane carbonyl chloride. All right, and we will get at least one example like this on our in-class assignment problem. When it comes to the nomenclature for anhydrides, it's pretty easy. Symmetrical anhydrides are super easy. You just name whatever the name of the acid is, the parent carboxylic acid, and just change the word acid into anhydride. And so an example of this is that this is derived from acetic acid. So if you take 2 acetic acid molecules and you get rid of the water, you will get the acetic anhydride. So again, just change the name from acid to anhydride. If you've got a mixed anhydride that has 2 different acid bases or acid components, so this would come from acetic acid, this would come from benzoic acid. You simply take the 2 names, put them in alphabetical order, and just throw the word anhydride at the end. So this would be acetic benzoic anhydride. When it comes to composition of an anhydride, that word anhydride just means without water. So quite literally, what we do is we take 2 carboxylic acid units and we lose water to get the anhydride. And so there are lots of examples of acid anhydrides. Just as one example is sulfuric acid is H2SO4. And if you remove H2O from that, you will get SO3. And SO3 is just sulfur trioxide. And so that's sulfur 6 oxide if you want to name it after the charge or the not the formal charge, but the oxidation number. So SO3 is just is the acid anhydride of sulfuric acid. And most of our acids we can do that with. Some of them get a little more complicated, but most of them we can do that with. All right, so let's look at nomenclature for esters. It's pretty easy. You just name whatever the R group is that it's attached to whatever your ester is. So like this is the R group. In this case, it's ethyl. And then the name of the acyl group, we're going to change the ending from ic acid to ate. So here we have an ethyl group. This part comes from acetic acid, so we're going to change the end of ic acid into ate, acetate. And then we'll put an ethyl out front with a space. So ethyl acetate. All right. This is a tert butoxy group here. A tert butyl group. We're going to keep the oxygen as part of this. So this is a tert butyl group, and that tert butyl group is attached to cyclohexane carboxylic acid. Well, we're going to change the ic acid here to ate, and so that will be cyclohexane carboxylate. So the whole name for this is going to be tert butyl cyclohexane carboxylate. All right, amides. We'll start with primary amides. And so all of our primary amides are pretty easy. If we just change the ending from ic acid or oic acid, like if we have propanoic acid, if we're using some of the common names, or ilic acid, if it's a carboxylic acid, we're going to change the ending to amide. And many times this is pronounced amide. In fact, I think probably more people pronounce it amide. I think I learned it from people who pronounced it amide, and then and once that happens, it's hard to say it another way. So just forgive me if most of your professors or other people pronounce it amide or amide. All right, so here, so this is kind of weird. So this is acetic acid derived from acetic acid, and so most people will call this acetamide, and that's usually what I call it. Even though I would call this an amide, I call it acetamide. So again, pronunciation, we're not here for strictly pronunciation purposes. We're here to learn how to name these things. So here, this is derived from benzoic acid, and we would change the OH to the NH2, and so we would call that benzamide. And then here we've got this 2-methyl the 2-methyl cyclopentane carboxylic acid derivative, and we changed it to the amine group, and so it'd be 2-methyl cyclopentane carboxamide. All right. Now, for secondary and tertiary amides, we're going to need to do one additional thing, and that is to indicate what alkyl groups are attached to the nitrogen. We indicate what those alkyl groups are by naming the alkyl group, or groups if there's more than one, bonded to the nitrogen atom, and then we use the letter N as a prefix to indicate where it is attached. And so, for example, here we have an ethyl group attached to the nitrogen, and this is the formamide, so we would call this ethyl formamide. So N-ethyl formamide. I forgot the N there. So N-ethyl formamide. And again, that N just simply indicates that the ethyl is directly attached as an alkyl group on the nitrogen. All right. So here we've got a benzoic acid derivative. So this is benzamide, and we have two methyls on there, and those two methyls are going to be NN. We do need to indicate because there are two. We'll need to put two N's there. So NN dimethyl benzamide. So NN dimethyl benzamide. All right, so our last thing here is just how we're naming all of these things, and it's just a summary page. So I'm not going to go over that. I am going to do problem number 34. On problem number 34, we'll be doing some naming. All right, so here is number 34. All right, so this, if it's a carboxylic acid, so if this were a carboxylic acid, we would call that cyclohexane carboxylic acid. So cyclohexane carboxylic acid. Since there's two and they are identical, we would call this cyclohexane anhydride, or cyclohexane carboxylic anhydride. So I'm going to write that out. So cyclohexane carboxylic anhydride. And there is a space between the carboxylic and the anhydride. All right, so here we've got, and I'm going to kind of circle this to indicate what our parent chain is. So this is based on acetic acid. So we've got acetic acid. So this would be an acetate because it's an ester. So we've got an acetate. We've got a phenyl that's attached to that acetate. It is attached to the 2 position, but since there's only 1 position it could be attached to, we're just going to call this whole thing phenyl acetate. And then if we come out here, there's a phenyl that's attached to the oxygen. Unlike with nitrogen, we don't put an oxygen, so we don't put or O phenyl. We just put phenyl. And so we'll say that this is, and I like to use the red for writing out the names. So we're going to call this phenyl space phenyl acetate. So again, it's acetic acid derivative, so that's why we call it acetate. There's a phenyl attached to it. That's this part, so that's the phenyl acetate. And then there's a phenyl attached to the phenyl acetate on the oxygen. So we'll put a space in between phenyl and phenyl acetate. I know that seems like a weird name, but that is an accurate name. All right, so let's look at the major component here. This is the amide or amide. Again, this is benzamide. So that's where we have a benzene with an amide functional group on it. So that's benzamide, and we have a cyclohexyl group on the nitrogen. So we're going to indicate that by putting N-cyclohexyl. All right, so N-cyclohexyl, and no space here, benzamide. All right, so N-cyclohexyl benzamide. All right, so now we've got an ester. And so our ester is based on benzoic acid. And so here, that would be the component that makes up the benzoic acid. So we're going to call that part benzoate. We're going to indicate where on there this chlorine is. It's on the 3 position. So 1, 2, 3. So on that 3 position, we have a chloro. So 3-chlorobenzoate. But then we need to put the methyl out front and put a space in between. So we're going to call that methyl for this methyl, space, and then 3-chlorobenzoate. All right, so methyl 3-chlorobenzoate. All right, next, as far as naming this, so we've got a cyclohexane, and then if this were an acid, we would call this whole component, we would call that whole component cyclohexane carboxylic acid. But we're going to call it cyclohexane carbonyl chloride. So that part is cyclohexane carbonyl chloride. So carboxylic acid gets converted into carbonyl chloride. So cyclohexane carbonyl chloride. That is going to be at position 1, and our bromo is going to be at position 2. So now, when we're naming this, we're going to put a cis out front because of the stereochemistry. So we'll put cis 2 bromo cyclohexane carbonyl, again, all one word here, carbonyl, and then finally space chloride. So cis-2-bromo cyclohexane carbonyl chloride. All right. And then finally on this one, we've got a cyclohexane. We've got a cyclohexane carboxamide, right? We would call this cyclohexane carboxylic acid if it were an acid. And so this is cyclohexane carboxamide. And we're going to put 2 ethyls on the nitrogen out front. And so we'll put N, N, because there are not methyls, those are ethyls. NN, diethyl, cyclohexane carboxamide. All right, and again, no spaces in there. That's all one big compound word. All right, so there we go. That is some nomenclature. So next, let's look at some physical properties. The physical properties for these are going to vary quite a bit, but they're all going to contain dipoles because they all have carbonyls in them. They're all going to have polar interactions. The ones that are going to be substantially different are going to be the primary and secondary amides. Those primary and secondary amides are capable of intermolecular hydrogen bonding, similar to what we saw with carboxylic acids. Now, with carboxylic acids, the hydrogen bonding was pretty strong. We got the dimer interactions. We can get those dimer interactions that occur with amides. In fact, that's a critical component for the link of base pairs in DNA. But we're going to find that we're going to look mostly at them as just some good old-fashioned hydrogen bonding. We'll find that the amides typically will have higher boiling points than the other carboxylic acid derivatives, like the acid chlorides, the esters, and the anhydrides. And the amides are going to be similar to the carboxylic acids. So acid chlorides, esters, ketones, aldehydes, all of those that are of about the same size are going to have very similar boiling points, melting points, those kinds of things. The amides are going to have much higher boiling points and melting points, similar to what we would see with carboxylic acids. All right, and we'll find as far as solubility, the water solubility typically happens when we have 5 or fewer carbons. And at 5, we're kind of on the edge. Sometimes we'll get things to dissolve, sometimes we won't. And it also depends on which thing we're talking about. Amides, yes, usually you'll get them to dissolve. Esters, maybe. It really just depends on all the various factors and how they all add up. But 5 is kind of our general cutoff for these polar compounds in their interacting with water. All of them should be pretty soluble in organic solvents. However, some of the ones with with a lot of these NH2 groups may be less soluble in some of our less polar organic solvents. All right, so let's look at the spectral properties. There's a couple of unique things, but there's also a lot of things that you've already seen over the past few chapters and going back to our spectroscopy chapter on infrared. So we know about the carbonyl stretching frequency. We're quite familiar with, or the wave number. We're quite familiar with that one. That's at about 1700 for our carbonyls. However, we're going to find there's a significant difference in the carbonyl stretching absorption depending on how stable the compound is. Or we can think of it as how basic the leaving group is. The more basic the leaving group, the more important those other resonance structures that we saw, the ones where we had partial single bond character in the oxygen. And so the more basic they are, the more important those other resonance structures are, and the lower the frequency and wave number is going to be. So for amides, which has a very good electron donating group on it, that means that we have a lot of single bond character. That means that the frequency is going to be lower, and therefore the wave number is going to be lower. So it's a weaker bond, and because it's a weaker, the carbon-oxygen double bond is a little bit weaker. That means that it will have a lower frequency. Now, when I say it's weaker, but the rest of the molecule is more stable because of that electron donating effect and the resonance effect. We go to esters, and we're going to find that they're very similar to the carboxylic acids, maybe a little bit higher than some of the carboxylic acids. We'll find for the acid anhydrides that those numbers tend to get up into the high 1700s and into the 1800s. We'll also notice that anhydrides have a double peak because of symmetric and asymmetric stretching. Whenever you have like a double carbonyl, it's not unusual to have two different modes where you have symmetric and asymmetric stretching. The symmetric is just where the bonds are stretching at the same time, and the asymmetric is where one bond is contracting while the other one is stretching, so it kind of goes back and forth. And so we'll get two different frequencies for that, and therefore two different wave numbers. For the acid chloride, it is typically up there at about 1800, and that's because there is a lot of double bond character. This is a less stable compound because the chlorine donates less electron density to it, and so therefore very, very strong double bond character. So we're going to find it's about 1800 instead of the typical 1700. So again, I do want you to know this, that where these peaks are for the different functional groups. One of the problems I like to give my students is where they have to determine what kind of functional group it is based on these absorbances. All right. Oh, and then for primary amides, we should have a double peak for the NH2. And for secondary amides, we will end up with just a single peak for the NH. So that NH shows up at about 3200 to 3400, similar location to the to an alcohol peak, but it's a different shape. It's not as intense as an OH peak, and it is so it's not as intense, and it's also not as smooth. It usually is kind of just a little bump. We do get a peak at around 1640 for amides, where we get what's called an NH bending motion. And again, we haven't talked about that, but that does occur, and since it's outside of the fingerprint region, I bring it up. So if you have an amide and you've got an unusual peak at about 1640, it's there for a reason. Now let's talk about NMR. So we will find that the hydrogens that are at alpha carbons on acyl derivatives all are going to be in that 2 to 2.5 part per million range. That is completely typical. We saw that with the carboxylic acids, aldehydes, ketones, and we're also going to see it with all of our derivatives. So that doesn't change very much. For hydrogens that are on a nitrogen, a primary or secondary amide, for those hydrogens, we will find that they fall in the 7.5 to 8.5 range. Now, that's not quite as far out as the aldehyde. It's not quite as far downfield as the aldehyde, but it is fairly downfield compared to most of our other functional groups. And so it's just a strongly deshielded hydrogen, so it's pretty far down there. You may recall for carboxylic acids, that number was out between 10 and 12 for the hydrogen that was on the OH. For our carbon-13, we're going to find that all of these acid derivatives fall in the 160 to 180 part per million range. So they're pretty significantly deshielded, which makes them fairly far downfield. They're not quite as deshielded as aldehydes and ketones, Most of your aldehydes and ketones are going to fall in the 190, even up over 200, sometimes 210, 215, whereas esters, amides, acid derivatives, all these acid derivatives are going to be more in that 160 to 180 range. So that's one tool you can use to distinguish between something that's an aldehyde or ketone versus something that is an acid derivative. Okay, let's look at number 38 on our in-class assignment. So we're going to switch over. Number 38, right here. All right, so propose an explanation for the difference in the frequency of the carbonyl absorption. And frequency here, we're meaning wave number, but okay. So for phenyl acetate, which is this one, it has a wave number at 1765. So 1765. And for the cyclohexyl acetate, it has a wave number at 1738. So this one is 1738. So we'll put those numbers in. So 1765 reciprocal centimeters for the carbonyl and 1738 reciprocal centimeters for this cyclohexyl acetate. Well, that's a pretty significant difference considering that these are both esters. Most esters are going to be closer to this. So what is it that makes this one different? So why is it that we get such a difference? Well, the difference is the quality of leaving group. If we look and we compare, go ahead and write this in regular color here. All right, so O minus, which is the phenoxide ion, its conjugate acid is phenol. And phenol has a pKa of approximately 10. So since that has a pKa of approximately 10, that means that this is a decent acid, not a super strong acid, but it's a decent acid, and so that this is a better leaving group than our other one. Our other one is the cyclohexyl hexoxide. I have to say that again. So cyclohexoxide. Its conjugate acid is cyclohexanol. Cyclohexanol has a pKa that comes in at about 16. That's a typical alcohol pKa. So right around 16. So that means this is not as good of a leaving group. So this one is a pretty good leaving group, and therefore, since it's a pretty good leaving group, it does not donate as much electron density to the carbonyl, which makes this have a higher frequency. This one is more in line with what we might see with an acid anhydride, or at least one of the peaks in an acid anhydride. Not quite as high as what we would see with a acid chloride, but that's definitely high for an ester, and it's all because this is a pretty good leaving group. It's less basic and therefore donates less electron density. All right, part B says, what carbonyl group is more effectively stabilized by resonance? All right, here we're talking about the carbonyl group. Which one's more effectively stabilized by resonance? And this one is going to be the one. So more stabilized by resonance. All right. Now, one thing I want to mention here is when it comes to talking about these leaving groups, this leaving group is definitely more stabilized by resonance, but that's not what the question is asking. The question is asking which carbonyl is more stabilized by resonance. And so since this is a stronger base, it donates more electron density and stabilizes the carbonyl better by resonance. All right, so that's what we mean. Which ester reacts faster when treated with aqueous base? Definitely this one reacts faster. All right, it has a better leaving group, so it will react faster. We're going to look at some interesting esters, carboxylic acids. Well, we've already done carboxylic acids, esters, acid anhydrides, amides, and those kinds of things. We're going to start with esters. There are many low molecular weight esters that have very pleasant odors, things that are quite characteristic. And so here are a couple of them. This one is isoamyl acetate, and it has the distinct odor of a banana. So if you think, oh, what is the smell that you think of when you think of a banana? Well, that smell primarily comes from isoamyl acetate. And so that's a very distinctive odor. Ethyl butanoate is a very characteristic smell that you might get from a mango. All right. The methyl 2-methyl butanoate, that one is the odor that you would get from a pineapple. And so it's one of those distinct odors. These are used extensively in things like perfumes. They'll put in small quantities in perfumes and in colognes and things like that. But they are also food additives that can be used to make foods have a little bit stronger flavor. So you might see these show up in very small quantities in things like candies and certain processed foods. There are some other interesting esters, including vitamin C and the ginkolide. Vitamin C is a critical nutrient. You have to have vitamin C in your diet. If you don't have vitamin C in your diet, you will get scurvy and all kinds of really unpleasant things will happen. And the ginkolide over here, this one is a terpenoid. It's got 20 carbons in it, and it's a very complicated molecule. And so there are different ones, the A, B, C, and D, and really the difference is like little things like different functional groups here, either a different OH or a different functional group here or something. So this has lots of biological activity. I think it's been used in certain cases for treating migraines, but I don't know how effective it is. Again, I am not a medical doctor. Talk to a medical doctor before taking anything new into your body. All right, interesting amides. We're going to look at some proteins and peptides. All the proteins and peptides that make up, that do all the hard work in your body. There's lots of enzymes and hormones and things like that are made up of polypeptides. They're just very complicated arrangements of many amino acids. Well, these are all going to have amide linkages. Now, the amino acids themselves don't have the amide linkage. Well, some of them do, but not all of them. But when you link them together, we get amide linkages, which we refer to as peptide bonds. And so there's a peptide bond, there's a peptide bond. So here we've got two glycines over there. I think that one's a tyrosine. Let's see, this one is phenylalanine there, and then this one is methionine. So when you put them together, you can get this. This is a naturally occurring opiate, and so it has some effects like morphine, although it is a little bit different, but it does have some effects like morphine. And there is a ball and stick model of it. When you get all these peptides with all these peptide bonds, the polypeptides, they have very complicated structures, and over time, as different organisms evolve and different enzymes evolve, these can have very specific jobs that they do in your body. So kind of cool. All right, antibiotics, and we would be remiss if we didn't mention antibiotics when talking about amides. There is a whole class. There's actually two whole classes that I am more aware of, but there are others that are related. But one class is the penicillin class of antibiotics, and you'll notice that all penicillin antibiotics are going to have this 4-membered ring, which is a lactam, a beta lactam. that's fused to a 5-membered ring that has a sulfur in it and has a carboxylic acid over here and has this particular stereochemistry at the alpha carbon, and that nitrogen is an amide. And you'll see this on all of the different penicillin derivatives, the different varieties of penicillin. There's another class of the cephalosporins that also have a beta-lactam. They also have that alpha, the stereochemistry, the particular stereochemistry at that alpha carbon with a nitrogen that is an amide. And they have a 6-membered ring over here instead of the 5-membered ring. But this is a different class of antibiotic that has given doctors more tools for treating infections. So they're always searching, scientists are always searching for new antibiotics, because a lot of antibiotics that we have started to lose some effectiveness against things that we thought were easily curable. And so they're looking for new antibiotics that are not going to be bacteria resistant or antibiotic resistant bacteria. So, all right. So we're going to do a brief introductory chapter to nucleophilic acyl substitution, which we've already talked about the mechanism for this. So we covered this mechanism, but I'm going to show it to you again, and I want you to know this mechanism by this point. When we're doing nucleophilic acyl substitution, the very first step is that the nucleophile is going to react with our carbonyl carbon. That will create a tetrahedral intermediate. That tetrahedral intermediate will then lose our leaving group, and we will get our new product. And we've seen this over and over and over again in chapters 17, not so much 18, but we did see it in 19, and we're seeing it again here in chapter 20. So this should be quite familiar at this point. When it comes to reactivity of carboxylic acid derivatives, which ones are more reactive and which ones are less reactive, we're going to find that, as we mentioned this before, but I'm mentioning it again, that as the ability of our leaving group increases, so as we get better leaving groups, we're going to find that the molecules get more reactive. And that makes sense. If the chloride can leave really easily, then that means this acid chloride is going to be more reactive. If it's very difficult for this, for the NH2 minus to leave, then this is going to be a less reactive molecule. All right. We'll find that we can, that when we have acid chlorides, they're very, very easy to convert into all of the other acid derivatives. When we have the amides, on the other hand, they are very difficult to convert to these other acid derivatives. And in fact, we have to do kind of a special trick to convert it to a carboxylic acid. And then if we want to get it all the way to a chloride, we have to do another reaction. But we're going to find this all depends on how good of a leaving group is Z. If Z is a good leaving group, we can do lots and lots of reactions. If Z is a very poor leaving group, like the NH2 minus, we're going to be limited in the number of reactions that we can do. All right. When we're comparing, like, is it a good leaving group? Really, what we're doing is looking at, is the leaving group better than what we started with? Is the nucleophile a better leaving group than our original leaving group? And if that nucleophile is a better leaving group, then we're not going to get much of a reaction. So, or we're going to have to do some more intense conditions like heat and pressure and things like that to get the reaction to occur. All right, so here I'm going to show you a preview of what's coming up in the next video, which is where we're going to look at these different types of acid derivatives. How do we make them, and what kinds of reactions can we do with them? And so and we're going to start with acid chlorides. We're going to break it down by group. Acid chlorides, we're going to find acid chlorides. They react with just about everything. And so we can make anything with an acid chloride. And so we'll talk about that in the next section. In the section after that, we're going to talk about anhydrides, and we're going to find that we can make just about anything with the anhydrides except for the acid chlorides. We'll also talk about carboxylic acids, which we can convert into acid chlorides with some tricks, but it's not going to be as reactive as these other things, so we have to use a trick to do that. And we'll talk about esters and amides. And we'll find that the amides are the least reactive, the ones that we have to sort of pound on the most with heat and intense conditions in order to get the reaction to occur. So we will be discussing all of that in the next video.